So we've reached the time of year where it's time to start thinking about a comprehensive exam and how that's similar or different from a regular unit exam. On a test of your entire knowledge, a lot of times they're not going to tell you what kind of question it is. They're going to expect you to look at a problem and pull out your knowledge almost like you'd pull out a wrench or a screwdriver, and you're going to have to figure out what task is appropriate for the job. In order to do that, we really have to develop what's called metacognition. We have to be thinking about how we think, and we really have to move away from just trying to learn facts. It's not about what facts do you know at this point. You guys have already shown you know the facts. It's about how do you know when to use them. So one thing I found in the past that has been helpful for students as they enter this phase of the year is to build concept maps in their head. And I want to do one for each of our units. I want you to think about what kind of problems could be asked in that unit and how you would recognize that at the beginning so that you know which tool to pick up. I feel like if we do these for multiple units and then we share them with each other, that's going to be a really good way for us to organize our minds, because that ultimately is the big goal at this point. How do we organize what's in our mind? So let's take an example of a unit that'll be on this year's test. And let's see how I organize it. And I'd like you to do something similar.
All right, so here's my concept map for Unit 5. I hope it makes sense. Do you have any questions? I'm kidding a little bit. Obviously, this looks like a complete mess. And this is the biggest problem with preparing for a comprehensive exam. You have been taught all of the facts. They have been thrown in your head. They have been stored there, but they're not in any sort of order. There are many connections between the facts you've learned in any given unit and in the course. But what you have to focus on as you're preparing is what are the links between those facts? What are the logical connections between them so that you can access them when you need them to? So obviously I can't just throw a concept map at you and say, here it is. You have to actively build this. So I'm going to try to demonstrate how to do this by walking you through where we need to, starting from the beginning. But ultimately, your success on this is whether you can build one of these yourself and see what the connections are. And that's why I think it's so important to do. So the way I like to start this is I ask myself, what are the big topics in a unit? And for the magnetism and electromagnetic induction unit, I thought these were the big questions. We learned about a new way that space is affected, magnetic fields. We learned how objects can experience forces in those magnetic fields. We learned how you can induce an EMF, which is kind of like a potential difference, and how that can cause a current. So I think every one of the problems fits into one of these categories. You might pick different categories, but at the end of the day, we just need to classify these problems somehow. So let's go through one by one and try to figure out what to do. So if they ask you a question about the magnetic field, I think there's basically two possibilities for what they can be asking about. They've given us information about a current carrying wire. They gave you the equation for the magnetic field due to a single current carrying wire. And just as a reminder, this is the magnetic field around a current carrying wire. And the fact that R is on the bottom of that equation tells us that as we move away from it, we expect the magnetic field to decrease. And we showed that in class. North in the class was basically this way. And as we got closer to the wire, the compasses aligned themselves in the direction we would expect due to the right-hand rule. The right-hand rule to find the direction of the magnetic field is pretty simple. You point your thumb in the direction of the current, your fingers curl in the direction of that field. So hopefully from those two pictures you can see that increasing current would give you a stronger field. Getting farther away, increasing the radius, would give you a weaker field. So that's one type of field we've talked about. We've also used the idea of magnetic field in the context of a lot of other problems. So you may be asked if you have information about force to figure out about magnetic fields. You may, if you have information about induced EMF or current, be asked questions about magnetic field. So you might want to be thinking about one of those other ones if it's not a current carrying wire. What if they ask us about force? Well, the big pitfall not to fall into is forces are forces, and you really have to start with Newton's second law. F does not equal ma. Sigma F equals ma. So if it's ever a force problem, you have to do a free body diagram. You have to consider all the forces, and you have to do sigma F equals ma equations for any dimension that matters. You know, sigma Fx, sigma Fy, sigma Fz, they're all different. You can't lump them all into one big equation. All of the care you took when you were doing mechanics, make sure you take that care now too. Make sure you haven't forgotten any forces. Those are some ones that often will be in there. I think electrostatics are definitely one to watch for because they love to combine those two ideas. And once you're sure you've gotten all your forces on your free body diagram, you've done all your sigma F equations, there's really only two possibilities for any magnetic forces. And let's take a look at those real quick. If it's a charge moving through a magnetic field, you can figure out the direction of the force by pointing your index finger in the direction of the charge is moving, curling your fingers in the direction of the magnetic field. The force will be in the direction of your thumb. And that's when you use this equation. FB is QVB sine theta. And we can see that if we had a magnetic field to the left here and we have a positive charge moving towards the top of the board, the force will be straight out in the z direction. If we turned and moved in the other direction, the force would be straight in. So magnetic forces are a little strange, and you do have to keep that right-hand rule in mind. The other one to think about is this stranger equation here. And this is if you have a current-carrying wire in a magnetic field. Which way will it feel a force on it? And we talked about that in the context of a railgun. So here's a railgun. We have conductive rails, which are hooked up across a potential difference. Remember that current comes out of the positive, flows around and back into the negative. So if you do the right-hand rule the way you were taught, treating the direction of current as the direction of imaginary positive particles, the right-hand rule tells you have a force in this direction. And the value of that force will be ILB sine theta. All that hopefully can help you with forces. And again, just make sure you're treating them like any other force problem. I think the second part of the unit is the one that has the least to do with previous physics we've done, so sometimes it can be confusing to students. But basically, if it asks you about induced currents or induced EMFs, you need to understand those are the same question. So you have equations for determining EMF, and there's no equation necessarily for determining the current. But basically what you do if you're asked about the current is you go back and find the EMF first, and then you use Ohm's law. Notice I've replaced the V here with the symbol for EMF, the script E here, and you can find current using that. So what do you do when it asks you about EMF? Basically, you're using Faraday's law. And Faraday's law says that when you change the magnetic flux through a coil, the faster you change that, the more EMF you induce. So if we take a look at that, here's the equation. N is left out on your equation sheet, but if you have more loops, you just multiply the effect by that number. And it basically says the faster you change the flux, the more EMF you make. So what is flux? It's the field times the area times the angle that the coil is making with the field. So just to make that a little clearer, if you had a coil that was facing this way and you were trying to change the amount of flux or the amount of magnetism inside, you could do a few things. You can make the coil bigger, it would enclose more magnetic field. You can make the coil smaller, it would enclose less magnetic field. You could actually just strengthen the field or weaken the field. That would change the amount of magnetic field inside. But you could also rotate the coil. So as I start to rotate the coil, I have less effective cross-section for flux to get through. And if I'm perpendicular to the field, none gets through. So that's why those are the variables that matter when you're talking about inducing EMF. So how are you going to calculate it? there's basically three ways that you could be asked about it. One of them is very specific. I have a wire that's being dragged perpendicular to two rails that are also perpendicular to a magnetic field. Oof. That's this strange equation, which I feel like we've used the least. And what's an example of that? Problem like this, where we're dragging a wire to the right, and if you look, the amount of flux inside is going to change because as that wire moves to the right, more magnetic field is going to be enclosed. So that's going to induce an EMF, and it's going to depend on the strength of the field, the length of the wire that's actually moving, and how fast you're moving it. So in that situation, you can think right away about using this equation. If you want any other situation where there's a quantitative answer, basically just figure out what delta flux is. So you can use the equation for flux, BA cosine theta, and just see how much it changes by. And then you can get EMF by doing the change in flux over the change in time. So that one, although I think it's more complicated because the idea of flux, the enclosed field, is a little new to us, it's actually pretty straightforward. Most interesting question is sometimes called Lenz's law, and it has to do with this little negative sign here, that's here. And what that says is that if you change the flux and create an EMF and a current, that new current is going to be created to oppose the change you made. I like to say that this is nature always fights you. So let's take a look at what I mean by that. And we'll use the picture we looked at a second ago to determine the direction of current as I drag that wire to the right. So let's take a look at how Lenz's law suggests that induced current will form in this loop as I drag this blue part to the right. As I do that, I'm going to be creating more inward flux inside the coil. So nature is going to always want to fight me, and that means it's going to want to try to create more outward flux inside the coil. So the direction of current, if you can imagine, I take my hand and I wrap it under that red wire right there. My fingers in the middle are pointing upward. So that's going to be the upward flux. And that means the current must be in the direction of my thumb. So that implies that Lenz's law says the current in the loop is going to be like this. And again, that's to fight the change I've created by taking this and dragging it to the right. So again, this is my map of magnetism and electromagnetic induction. Yours might be different. And that's okay. But the point is I have connections between these ideas, and you need to have them too. So that's why we're going to take some time to make these connections so that you have an organized way of using your thoughts.
So anyway, I hope you found that helpful. I think as you start doing this yourself, you're going to find it very helpful, and you're going to feel like it adds an extra layer of your understanding. I'm also excited for the chance for us to share our different ways of organizing each unit, because I think as we try to explain why ours are similar or different, that's going to give us a depth of understanding too.